Hi students, today we're going to be discussing another state of matter, which is the liquid phase. So we're going to be talking about what the properties we can expect to see in liquid matter would look like and what those liquids probably have in common. It's important to state at the beginning that liquids are in the medium amount of kinetic energy. They have less kinetic energy and therefore less motion than their gaseous or gas counterparts, and a lot more motion, though, still than solids that have only vibrational and rotational movement. So liquids can still diffuse, which is to move past each other based on their random motion. They can evaporate, which is they can go to the gas phase. They can form solids, so they can go to the solid phase, and they can also create surface tension. This is important to include for a complete list of the properties of liquids, but surface tension becomes a much larger priority for us in chapter 15. So we're really not going to talk much about surface tension today. We're going to be concentrating on the properties of liquids that lead them to phase changes. So we're going to be really concentrated on the evaporation and the formation of solids. So the first property of liquids that we're going to be looking at today is that liquids can diffuse. So remember that gases also diffuse, which is mixing based on their random motion, and liquids do the same thing. So liquids are going to mix with one another based on their random motion, and you can do a little example to demonstrate this even in your own houses if you wanted to. If you were to take a glass of liquid water and add just a single drop of food coloring into that glass, at the beginning, the water molecules would be concentrated around the edges of the glass, and the dye molecules would be concentrated within the food coloring that had just entered the liquid. But as time progresses, those water molecules are going to move via their own random motion and will eventually, as time passes, they'll start to spread out. And eventually, given enough time, maybe an hour, you would see that these molecules would have evenly distributed throughout the glass. So those water molecules would be moving using their random motion, and they would be diffusing or mixing up with other liquids. This happens as a function of kinetic energy, which remember means that warmer things move faster. So if warmer liquid is moving faster, then warmer liquids would diffuse faster than a cooler liquid of the same material. It just has to do with the mixing up at a quicker rate because the molecules are just moving at a faster rate. Liquids also, very importantly, can evaporate. So one important property of being a liquid is that it can become a gas. So when we talk about evaporation, we are talking about liquid molecules at the surface of the liquid gaining enough energy to escape. So this happens, evaporation happens at room temperature or below the boiling point. The boiling point is the temperature where all of the liquid wants to go, leave, and become a gas. That's not what we're talking about here. Evaporation happens at room temperature, where our liquid molecules gain enough energy to leave and go become part of the gas phase. If you wanted to speed up evaporation, there are three main ways to do it. You could heat it. So I'm not talking about heating to a boiling point. What we are talking about is if you were to, let's say, spray perfume on your neck, the warmth of your neck, the warmth of your body would get the solvents in the perfume to evaporate a little bit faster. So if you spray the perfume on your skin on a warm day or when your skin is feeling warm, the solvent will evaporate faster than if you sprayed it on a cool day. Another thing you could do would be to increase the surface area. Because evaporation happens at the surface, the more surface area something has, the quicker it will evaporate. Back in what feels like the olden days, when you students used to come to class and we were allowed to eat in the classrooms, students would often bring like a Starbucks or something into class. And if you're to put that Starbucks on the table, when you go to leave, you pick it up, there's often that condensation ring that's on the desk. And conscientious students would notice that and be like, oh no, like I'm sorry, I left a ring here. And what you could do, even without a napkin, is if you just take your hand and you just wipe it, very quickly it will evaporate away. You also see this sometimes in basketball games or volleyball games. If there's a really long play or it's late in the game, the players are sweaty, and someone dives or falls onto the ground and they leave like sweat on the floor, you'll see the other players kind of stand around and they pull the sweat with their shoe. What they're essentially doing is they're increasing the surface area. They're spreading out the liquid so that there is more surface. And if there is more surface, then there is a greater chance for that liquid to evaporate. The last thing that we could do is we could add wind. And if you've ever painted your nails, quarantine has given us the chance to do that a lot, right? If you've ever painted your nails, you may recall going like this in order to get them to dry. The idea here is that you are exposing, you're creating wind, right? If you add wind, you're actually providing a little bit of extra energy to those particles to help them leave into the gaseous state. And you know that, same thing if you wash your hands but don't have a towel to dry them, you might flap them in the air in order to help them dry off a little faster. You may also know, it says so right on the hands dryer, that you're supposed to rub your hands together while you're drying your hands. That's because you're increasing the surface area. So all of these things are ways that we can increase the rate of evaporation. Now, before we can go on to talk about what happens once those liquid molecules become gases and the partial pressure that they make, we just need to start by considering what happens when you put water in a closed container. And so what we call this is a closed system. So if I have my water in a closed system, that means that I have some water in here and I've closed the top. And so no water can escape, and it's just going to exist here now, sitting, waiting for equilibrium. So let's consider what's happening to the molecules inside of that water bottle. So as we create the water bottle, some of the high energy molecules on the surface are going to want to evaporate. They're going to want to become a gas, even though they're not at their boiling point. And at the same time as some of these water molecules, you can see their little like green tails saying that they're like going up, they're getting energy. At the same time, other water molecules are going to, as they are in the gas state, are going to crash back down into the liquid water. When the number of water molecules that are leaving is equal to the number of water vapor molecules that are condensing, we say that this water bottle is in equilibrium. And you can kind of see that some little droplets of water have come into contact and are staying on the surface of this water. What that can tell you is that I don't drink enough water. I have my water bottle sitting next to me, but it's just been sitting here for most of the day. And so it has established this equilibrium where some of the water molecules have evaporated to become gas and some have condensed back down. Some have condensed on the side, making some condensation. If you ever get into your car, maybe after you left a water bottle overnight, and you notice all the little droplets along the surface of the inside of the water bottle, that's because it has reached an equilibrium. And so the water molecules that have evaporated have condensed on the edges of your water bottle. Once those water molecules have evaporated, they now are contributing a pressure to the system. So we already talked about what pressure was, right? Pressure is collisions of the gas particles with the container wall. So what we've done is, as we've heated the container, we have created more gas particles, and more gas particles mean more collisions. Imagine if you were driving on an empty road, you have a very small chance of running into another car. But if you're driving on a very, very busy street, your chances are much higher of getting in a car accident. That's what we're talking about. We're talking about an increase in number, increasing the chances for collision. So these water vapor molecules are now creating more collisions. And so we call those collisions the equilibrium vapor pressure, the amount of pressure that the water vapor creates or extends onto the container walls when it starts colliding with them. So as the gas evaporates into the gaseous state, it creates a vapor pressure. Now we can change the equilibrium and we can start to make more water vapor. If I take that same container and I start adding kinetic energy to the container, and remember the way that I would add kinetic energy to the container is that I would heat it up. That system is going to have to shift to a new equilibrium. As I increase the heat, the liquid water is going to become water vapor. And then that water vapor is going to start colliding with the container walls. And so we will be creating more and more pressure. You know, hopefully, that you should not heat a closed container. It will explode. If I were to take this water bottle, and let's just pretend that it was not going to melt, okay, I was able to heat it without melting the plastic, eventually the pressure inside should explode the bottle. So we say that the more heat will shift the equilibrium to the right, to the products. So as we continue adding heat to the solution, we can shift the equilibrium so that we get more vapor pressure, but we establish a new equilibrium. If we continue heating, and this would require us to open the container, but if we continue heating our liquid, eventually the amount of energy that all of these water molecules have causes them to all want to leave concurrently, simultaneously. They want to go. And that means that the energy that they have is equal but opposite to the atmospheric pressure. So the vapor pressure up here has become equal or opposite to the atmospheric pressure. At this point, all of our liquid molecules all want to evaporate at the same time. And so we say that the liquid is boiling. When a liquid is boiling, you will be able to see bubbles throughout the liquid because the bubbles can rise, can form, because the vapor pressure can overcome the atmospheric pressure. So the pressure of these little liquid molecules wanting to leave can overcome the atmosphere that's pressing down on them. When we're talking about evaporation only, we don't see any bubbles that have formed. So when we're talking about evaporation, there are no bubbles in the container. So if we can add heat and raise the vapor pressure and increase the amount of liquid that's becoming gas, we can also decrease the heat, drop the heat down, and force our gas molecules back into the liquid state. So as we start to cool the gas, as we start to cool the container, the molecules lose energy. And as they lose energy, kind of like when Dorothy is running through the poppies, right, as they're on their way to the Emerald City in The Wizard of Oz, and she starts to get so tired, and it's like, well, we're running, no, we're walking, no, we're laying down, we're so tired. That's what happens as you start to cool the molecules. So those molecules that were running around inside of the gaseous state are now cooling down, they're losing their energy, and they're going to fall back in to the liquid state. So when we cool the liquid, when we lower the heat, we shift the equilibrium back to the left. And if we keep doing that, if we keep decreasing and decreasing and decreasing the heat, we will eventually reach a point where the liquid even starts to lose too much energy and it can no longer even stay liquid and it's going to start to reach the freezing point. So the temperature where liquid of a substance becomes a solid is known as the freezing point. So as you continue lowering the temperature, the energy of those molecules also lowers. And so they no longer have the energy to move past each other, to slide past each other and diffuse, to take off and evaporate. No, they're out of energy. They're so tired. I picture those characters from The Wizard of Oz as they go through and they're getting so tired and they just eventually they're just asleep. And so now we end up with this physical change from the liquid to the solid. And at this point, we've now created a solid, which is a property of a liquid, that it can form a solid. It's also a property of a liquid that it can form a gas. So now we've formed this solid, and in our next video, we will spend some time looking at what the properties of a solid are. What happens when we've decreased that kinetic energy so much that the molecules can no longer even move past each other, and instead they only vibrate and rotate around a fixed position. So that's what we're going to talk about the next time we meet up. I'll see you in class.